Sometimes we'll have a sound cue that is playing several different audio tracks, and we want to use frequency analysis on each of those tracks independently of the others. In this video, we'll look at how to use the frequency analysis of different music stems to control different particle systems. In Area 4 of the demonstration level, we have a magical cutscene that we looked at before in the envelope analysis video. So walking over to this area and pressing Q instigates the cutscene. In the previous video, we looked at how you can analyze the envelope of a sound and use this cooked data to affect the real-time appearance of the woodwind and tuned percussion stems of this piece, which you can solo using keyboard key 6. This time we're going to look at how you can use frequency analysis of individual stems, and we're going to focus on the brass and percussion stems. You can solo these sound waves and their accompanying emitters using the keyboard key 7. If we open up this blueprint, the Magic Cutscene Controller, you can see that again we're using the same sound cue that we used for the envelope analysis. This time we've focused on the lower brass and lower percussion stems. In each of these stems we've enabled baked FFT analysis. For the lower percussion, we're analysing frequencies 86 Hz and 13.5 kHz. Looking at the spectrum of the sound in our audio editor, I've added a bandpass filter, and you can hear how 86 Hz is going to allow us to pick up on the bass drum events. And 13.5 is going to give us the cymbals. For the lower brass, we're going to analyze the magnitudes of the sound at 123 Hz and at 1800. So that's going to allow us to separate out the activity of those lower trombones and the upper trumpets. Dragging out from our audio component, we're using the Get Cooked FFT data for all playing sounds. Unlike the Get Cooked FFT data node, which returns the average magnitude at a given frequency for all sounds that are playing on an audio component, the Get Cooked FFT data for all playing sounds allows us to extract the frequency magnitude data for each specific stem or sound wave. So what it's actually returning is an array of structs. Each frame will be getting 4 elements in our array that correspond to the 4 sound waves within our sound cue. As we break open these 4 structs in turn, using the for each loop and this break node here, we'll get the reference to the sound wave object, the playback time of that sound wave, and another array that contains the structs with the actual current spectral data for this sound wave. This again is an array of structs, since we may have defined several different frequencies to analyze. In our case, we defined the 87 Hz and 13.5 kHz for the lower percussion, and the 123 Hz and 1.8 kHz for the brass. If we add a print string here at this point, what we can do is get a readout from the sound wave display name, which should show us the 4 elements in our initial array. By getting the name of the sound wave and checking against the substring brass, we're able to get the spectral data when the for each loop is giving us the brass data. And if it's not the brass data, in other words if this is false, then we check whether the name matches the percussion stem, and if so we then get that data. Using these substrings or finding text within text is really useful, since it allows us to identify certain groups of sound by name. For example, if we wanted to route the data of both the brass and the percussion to a particular item, we could then check the text for the substring cutscene lower, since both these sound waves contain these texts, so they'll both result in the branch being true, and so the data will be collected. So, if the name in this instance contains the string lower percussion, then the branch is true. Then we need another for each loop to read the packet of data for each frequency that we defined in our sound wave. In this case, there's only two, one for the 86 Hz and one for the frequency of 13.5 kHz. So for each of these, we check whether the current struct contains that frequency, and if true, we send the magnitude of that sound wave at that frequency to the particle systems within our emitters. Let's take a look at the magnitude range we're getting for audio events at this frequency of 86 Hz. So we'll add another print string here, and we'll look at magnitudes. And we'll turn this initial one off. This time I'm going to solo just that lower percussion stem using the keyboard key 4. So looking just at these magnitudes when this returns a frequency of 86, we then apply this to our emitters. This is an array of emitters, it's a public variable, so that means it's available here in the viewport, and we've been able to use the picker and select the particular emitters we want in the game. Using yet another for each loop, we go through each of those in turn, and we map the magnitude of the frequency to a range between 0 and 1, using those magnitudes that we just saw via the print string. And this is used to multiply a color variable called Cloud Percussion 86. Now color variables have default ranges between 0 and 255, so we've divided this by 255 in order to get the range we want, which is between 0 and 1. We've chosen 0 and 1 because the parameter we want to control within the emitter's particle system is expecting this range. So back in our viewport, we've got one of those emitters selected, and we'll open up that particle system. And here we're controlling this parameter called Cloud Color, and you can see that it's expecting a range between 0 and 1. For these colors, 0 is 0 intensity, which is black, and 1 is full intensity, which is white. And the effect it has within this particle system is that the closer you get to black, the more transparent the particle becomes. We've added a power function here just to get a more nonlinear extreme response to the values. So the 86 Hz relates to our bass drum frequency, and let's just take the R value here and add that to the print string, and we can correlate that value changing with the visual image which should accompany the bass drum. So let's watch particularly the pink cloud emitters. And you could also note there the blue cloud emitters which are responding to this frequency of 13.5 kHz. And the same methods applied in order to control the transparency of that particle system. If we look quickly at the brass, that's controlling the green beam and the purple beam in the game, and you can see it's got a very similar system. This time we're checking the name of the current element, and if it's got a substring brass, we then break that data, and we check that against values of 123 Hz and 1.8 kHz, and we route these magnitudes here to the green beam and the magnitudes at 1.8 kHz to the purple beam. And these beams should relate approximately to what the lower trombones and the higher trumpets are doing. So this time keyboard key 3 should isolate the brass. And let's finish by seeing those two things in combination. So we've got our sound cue, and we're looking at these two stems, and from those two stems we're analysing two frequencies from each. The two frequencies from the brass stem are being used to control the green and purple beams, and the two frequencies from the lower percussion are being used to control the two clouds, one that relates to the bass drum and one that relates to the cymbals. So we'll press keyboard key 7 to see those two stems in combination. In this video, we've seen how we can access the spectral data of individual sounds even when they are playing together within a sound cue.